In this lecture, we will discuss about finite group. So in finite group, we define as let G be any set under the binary operation who G with binary operation, the algebraic structure is said to be a finite group if G be a group and G has countable element. G has countable element. That means G satisfy all the properties of group and G having countable element means finite number of elements. So then G is said to be finite group. For example, suppose we take the set of integer. We take the set of integer. Set of integer consists the elements in this way: 0, plus minus 1, plus minus 2, plus minus 3, plus minus 4, and so on. So this type of group is called infinite. This type of group is called infinite. Similarly, set of rational number we denoted as q as p upon q, where q is not equal to 0 and both p and q are belongs to integer. Be also the example of infinite group. So for finite group, it is necessary the element of G should be countable. For finite group, G must contain the finite element, must contain the countable element, contain the countable elements. Countable elements. Now we take the example related to finite group. So very popular examples for finite group. So prove that G is equal to 1 omega omega square be an abelian group under multiplication under multiplication with the cube root of unity with omega q is equal to 1. So omega q is equal to 1. So that means we shall prove that this finite group is a finite set is an example of the group. So when we prove this, so we make a composition table. So this is the best way to prove that. So that means for making the composition table under the multiplication operation. So we take the element 1 omega square 1 omega omega square. So we do the multiplication. 1 into 1 is 1. 1 into omega is omega, and 1 into omega square is omega square. Omega into 1 is omega. Omega into omega is omega square. Omega into omega square is omega cube, or omega cube is equal to 1, cube root of unity. So this omega cube we can write down as 1. So omega square into 1 is omega square. Omega square into omega is omega cube. So this can be written as 1. Omega square into omega square is omega raised to the power 4. So omega raised to the power 4 can be written as omega cube into omega, or omega cube is 1, so 1 into omega gives us omega. So this omega 4 can be written as omega. Okay, so hope you understand this composition table. Now, under multiplication, so for closure property, we see that we have done the closure property. So that means all the element is this table also belongs to the set G. So also belongs to G. So that means closure property is satisfied. Okay. So closure property satisfies. Otherwise, you can write down the closure property. So we write down as closure property. So for closure property, so we take any two elements. So suppose we consider A equal to 1 and B equal to omega square. So when we write down as A into B equal to 1 into omega square gives us omega square, or omega square be the example of G. So you can take any two elements. So that means as per composition table. So when we do the product of any two elements, so gives the uh, element of the same set. So that means this is the example of group. So all the elements, so these are all the element also belongs to G. So that means closure property satisfy for all the elements. So we can write down as closure satisfied. Closure satisfied. Similarly, we do for the associative property. So that means we can take any three elements. So suppose we consider as A equal to 1, B equal to omega, C equal to omega square. So now when we do A into B into C is equal to A into B into C. So this can be written as 1 into omega square equal to 1 into omega. So 1 into omega into omega square. So also satisfy. So that means you can write down 1 into omega cube is equal to omega into omega square. So omega cube is equal to omega cube. So omega cube equal to 1 cube root of unity. So satisfied. Okay, so this is not necessary you take the different or distinct element. You can take the same element also. Same element means suppose we are considering A equal to omega, also considering B equal to omega, we considering C equal to omega square. So give the same results, means satisfy the associative property. So you can write down as omega into omega square is equal to omega into omega square. So this gives us omega into omega cube is equal to omega square into omega square. So omega raised to the power 4 equal to omega raised to the power 4. So omega 4 gives us omega. So satisfied. So associative property also satisfied. Now we move to the third property, that is the identity. So third property, identity. Identity means 1. Multiplicative identity 1. 1 belongs to G. So when we do the product of 1, so that means A into 1 is equal to 1 into A gives us always A. So you can see that from the composition table. So this is 1 we consider as the multiplicative identity. So when we multiply, that means 1 into 1 is 1, omega into 1 is also omega. That means this can see that column and row as per the both element, this two or this element. So that means give the same element of G. So that means when we consider A is equal to 1, so 1 into 1 is equal to 1 into 1 is equal to 1. So this one also belongs to G. Suppose we consider A equal to omega. So omega into 1 is equal to 1 into omega gives us omega. Omega belongs to G. So that means satisfy the property of identity. So when we consider A equal to omega square, so this also gives us omega square into 1 equal to 1 into omega square is equal to omega square. So we can write down as identity satisfied. So identity also satisfied. So when we do the product by 1, so give the same element. Now we move to the next property, that is the inverse. So for inverse, so we use the table. So when we use the table, so we see that the how we have the identity elements. So where we have the identity, this is the identity element 1 in the particular composition table. So here is also the identity element 1, and here we have also identity element 1. Now as per the identity elements, we see that the where is the image of identity element. So that means from we start this side, so we see that the image of this 1 from identity is 1. So the image of 1 is 1. The image of omega as per the identity element is omega square. And image of omega square as identity element is omega. So now the inverse of 1 is 1. Inverse of omega is omega square. And inverse of omega square is omega. So composition table, from composition table, the inverse of 1 is 1. Omega is omega square, or omega square is omega. So now we shall prove that the property of inverse, A inverse into A into A inverse into A is equal to 1, means identity. So when we take as 1, so 1 inverse is 1 is equal to 1 into 1 gives us 1, satisfied. When we take omega, and omega inverse is omega square is equal to omega square into omega gives us omega cube, or omega cube equal to 1, cube root of unity. So this also satisfied. That means inverse satisfied. So we have taken the inverse that are correct. Now third one, when we take omega square, so the omega square inverse is omega. So we write down omega into omega square is equal to omega cube is equal to 1. So the inverse satisfied. So inverse satisfied. So we can write down as multiplicative inverse of 1 is 1. Multiplicative inverse of omega is omega square, and multiplicative inverse of omega square is omega. These all element also belongs to the group G. So it means the given group, so hence G is an abelian. Oh, sorry, G is a group. So G is a group. G is a group. Now we move to the further property, means fifth property. So that is commutative law. Commutative law. So for commutative law, we see that A into B is equal to B into A. So also satisfied when you consider A is equal to omega, and B is equal to also omega. So we can see that omega into omega is equal to omega into omega, means omega square is equal to omega square. Or you can consider A equal to omega, B equal to omega square. So gives us omega into omega square is equal to omega square into omega. So omega q is equal to omega q, means 1 is equal to 1, satisfied. So you can take any element. You can take repeated element, or you can take different elements. So always satisfied. So hence we can write down as hence G under multiplication, under multiplication is an abelian group. Is an abelian group. Okay, so remember these are the uh, questions for finite group. Now we take some example related to finite group. So G is equal to singleton set 1. G equal to 1 is an abelian group. Remember, is an abelian group. under multiplication. Under multiplication. This is the singleton set is always an abelian group under multiplication. That means identity element satisfied, 1, and inverse is 1, also satisfied, and closure associative and commutative is also satisfied. So remember, G, finite set with single element 1 is an abelian group under multiplication. Under multiplication. Now, second example. Second example, G is equal to 0. G equal to 0. Single element 0 is also an abelian group. Under addition. Now, we move to the next example. So, next very important example, we will use this example in various cases. So, prove that G is equal to 1 minus 1 iota minus iota is an abelian group, is an abelian group under multiplication. So, we also prove this group, this is G set G is a abelian group under multiplication. So that means given G is equal to having 4 elements means finite set 1 minus 1 iota minus iota. So we shall prove this set is also abelian under multiplication. So we make again the composition table. Again the composition table with respect to multiplication. So we take the element 1 minus 1 iota and minus iota. So 1 minus 1 iota and minus iota. So when we do the product of 1, 1 to 1 is 1. Product of 1 or minus 1 is minus 1. 1 into iota is equal to iota. 1 and minus iota is minus iota. Minus 1 into 1 is minus 1. Minus 1 into minus 1 is plus 1. Minus 1 into iota is minus iota. Or minus 1 in minus iota into iota. So iota into 1 is iota. Iota into minus 1 is minus iota. Iota into iota I square. I square is equal to minus 1. Iota into iota I square minus 1 minus minus plus 1. Minus iota into 1 is minus iota. Minus iota into minus 1 is iota. Minus iota into iota I square is equal to minus 1 or minus minus plus 1. So I square is equal to minus 1 or minus minus plus means minus 1. So this is the composition table. So again, we see that the composition table, all the element of the composition table. So that means all the element of this composition table belongs to the G. So that means closure is directly satisfied. So when we write down the closure property, so for closure you can write down directly. So the composition table contain all the element of G. Contain all the elements of G. So means closure satisfied. Closure satisfied. Closure satisfied means you can take an example if we consider as a equal to 1 and b equal to iota. So when we do the product of a into b, so 1 into iota gives us iota or iota belongs to g. These two also belongs to g means closure satisfied. You can take any two elements. So from the composition table, we can say that all the elements on the composition table belongs to G. So closure satisfied. Similarly, we do for the associative. So associative, so that means we can take three elements. So A equal to we consider as 1, B equal to we consider as iota, C equal to we consider as minus iota. So A into B into C is equal to A into B into C. So we can say that 1 into iota into minus iota is equal to 1 into iota into minus iota. So 1 into I square is minus 1 or minus minus plus 1 is equal to iota or minus iota. So iota square equal to minus 1. So this is 1 minus minus plus 1. So 1 equal to 1 satisfied. Okay, so always remember iota square equal to minus 1. Now we move to the identity. So from the composition table, you see that the 1 is the multiplicative identity which is belongs to G. So when we do the multiply any element by 1, so that means this is our 1 and we multiply by 1, so give the same element of G. So that means identity satisfied. Either you can take this first column or you can take the first row as per this element. So the elements are belongs to set G. So that means identity satisfied. So identity satisfied, you can take as a suppose a equal to I. So we can write down a into 1 is equal to 1 into a is equal to a. So iota into 1 uh, iota into 1 equal to 1 into iota gives us iota, which iota belongs to G. So identity satisfied. Okay, there is no need. That means we have represented in the composition table. So that is sufficient. So identity satisfied. Now we move to the fourth property, that is the inverse. So for inverse means we have a into a inverse is equal to a inverse into a is equal to 1 means identity. Now, how to obtain the inverse? So inverse we can obtain directly by using the identity. So that means here we circle the identity elements in the composition table. So these are the identity element. Now we see that the image, that means the element 1 for identity element having image is 1. So inverse of 1 is 1. Minus 1 having the image is minus 1. So minus 1 inverse is minus 1. And iota inverse is minus iota. And minus iota inverse is iota. So we can write down the inverse. So as per composition table, so that means the inverse of 1. 1 inverse is 1. Minus 1 inverse is minus 1. Iota inverse is minus iota. And minus iota inverse is iota. Now, we shall prove this. That means by using this, our inverse property satisfied or not. So where that means first case we can take as 1. So 1 inverse is 1. So 1 into 1 is equal to 1 into 1 gives us 1, means satisfied. Second, we take element minus 1. The inverse of minus 1 is minus 1. So we can write down this as also satisfied. So third, we can take as iota. So what is the inverse of iota? Iota inverse is minus iota. So we can write a minus iota into iota. Or iota square is equal to minus 1 or minus minus plus 1, means satisfied. Fourth one is we can take as minus iota. The minus iota inverse is iota. So we can write as iota or minus iota gives also equal to 1. So satisfied. So hence the inverse, this also belongs to G. So that means we can write down as inverse satisfied. So when inverse satisfied, so we can say that the given set G is a group. So G is a group. So G is a group. Now we prove that the fifth property, that is the abelian group. That means commutative. Commutative. So for commutative property, this is hereditary, also hold. So A into B equal to B into A. So suppose we can consider as A equal to iota and B equal to minus iota. So iota into minus iota is equal to minus iota into iota. So this equal to 1 satisfied. So you can take any two elements, any two element of the set G also satisfy the commutative property. So hence the group, that means the G is equal to 1 minus 1 iota minus iota is an abelian group, is an abelian group under multiplication. So you remember this example for further topics.